This is Module 3 of Engineering Vibrations 1, an introduction to vibrations, looking at single degree of freedom systems. Our outcome for today is to develop the second of the three system elements that we talked about. This one will be the spring, and it's used for modeling vibratory systems. Last module we talked about mass, and in the future we'll talk about dampers. And so just as an overview, you can see the actual system and the physical model in the center. This is what we're doing now. We're looking at those three elements, masses, spring, and dampers, which is shown under the physical model. So for the spring, we're going to look only at linear springs, as I said in our assumptions in the last module. And here is a linear spring. We subject it to a force. You probably saw this in your physics classes. You subject the spring to a force and it elongates. It starts from some unstretched length and then it pulls out to some fully stretched length, the initial unstretched length plus some delta. And the spring constant is given in newtons per meters or pounds per foot. That's the characteristic of the spring. We're going to assume again that it's linear, so there's a 1-to-1 ratio, actually not 1-to-1, but k-to-1 ratio of the force to delta, and that gives us our spring equation that the force in the spring is equal to k delta, the spring constant times the delta, which is the distance either expanded from or compressed from the unstretched length. So I'd like to do a couple of examples here with springs. Here's a typical spring. And you can see that I can either stretch it, and I'd have some F equals K delta for the amount of stretch, or I can compress it. And again, we're going to assume, although it's really an oversimplification, that K in both tension and compression is the same. Here's another example. This is a stiffer spring. Not a stiffer spring, a spring that is longer and will stretch more. And you can see, in this case, I'm just going from the unstretched length in tension. I'm not able to compress this spring. Here's another spring. I'd like to give you some different examples. This is a linear spring with a very soft spring constant, so you can pull it apart. Okay, so that's linear springs. Now we also can have torsional springs for angular motion instead of linear motion. And so here is an example of a torsional spring. You might think of this as torsional springs in a watch. If you've ever taken a watch apart, an analog watch, you can see a torsional spring in there. And I'm going to give you an example in a second so you can see the torsional spring action. Here we have a K sub T, so it distinguishes it as the torsional spring constant. And again, there's a linear relationship between now the moment being applied to torque the spring and the angular displacement, theta. So here's the equation that's associated with a torsional spring. The moment from the spring is equal to the torsional spring constant times the amount of angular displacement. And so here's an example, okay? If I twist this spring, you can see there's a torsional, I'm putting on a moment, and there's an angular displacement that's related to the spring constant of the torsional spring. So that's the element of springs, and that finishes up this module. We've developed the second of the three system elements, being the spring that's used for modeling vibratory systems.